I'm going to talk about the Rogers theory of dementia. This is my theory. I'm Peter Rogers, MD, Dr. Rogers. And I spent a long time trying to figure this out. And it started when, and by the way, I've written in much more detail in this one book of mine called Food, Mood, and IQ. And I added additional information on it in my other book, Prevent and Reverse Chronic Fatigue Syndrome. I go all through the beta amyloid theories. I go through the phosphatidylserine externalization stuff, etc. in those books. And I give in other YouTube videos where I go in all of these in more detail and I show all the slides. But this talk is unique in the sense I'm going to summarize the whole thing for you. Because I talked to some doctors about this and none of them knows any of it. And so I'm going to give them a quick summary if they want to get the point from this lecture. Okay, first of all, it started with, I see tons and tons of demented patients. Dementia is like saying, good morning. That's how often I see dementia. I see dementia all day long, every day. I have internal medicine doctor buddies. They tell me, a couple of them, all their patients over 60, they're all cognitively slow. Okay, dementia is becoming more and more common. And then, you read the stupid neurology literature. It's half retarded. It's fake. They go, oh, Alzheimer's is the most common. That's all BS. There is such a thing as familial Alzheimer's that is a real thing, but almost all of this sporadic Alzheimer's is just nonsense. They totally exaggerate it as a way to get more funding. If you can say, oh, Alzheimer's is the most common cause of dementia, please give us more money to study Alzheimer's. I don't even really think it exists. Let me explain why. Because you can't diagnose it when the patient's alive. There's no question you can ask the patient. There's no physical exam finding. You can't put your stethoscope on the patient and diagnose Alzheimer's. There's no reliable blood test. Even at autopsy, the findings aren't that reliable. And they have no treatment for it. So what would you call a disease that you can't diagnose it when the patient's alive, you can't diagnose it when the patient's dead, and you have no treatment? You would call that a BS disease, okay? And I look at the brains. I'm a neuroradiologist is one of the things that I do. I'm board certified in 3 fields. And I don't see the characteristic so-called Alzheimer's pattern of parietal temporal atrophy. I see diffuse cerebral atrophy all day long, every day, nonstop. I don't even have to look at the films. I can put them, it's in my template, diffuse cerebral atrophy, because that's what I almost always see. And, occasionally I'll see multi-infarct dementia or something else. I almost never see, dementia caused by communicating hydrocephalus, normal hydrocephalus, or tumors. I see a meningioma brain tumor, benign brain tumor causing dementia about once every 15 years. Okay, that's how rare it is. All right, all day long. Global atrophy, global atrophy, global atrophy. Okay, so anyways, why does the brain shrink? Why is it that I'm looking at shrunken brains all the time? And I'm going to tell you, here's the big secret of that. The reason you have cerebral atrophy is because the cells undergo apoptosis, programmed cell death. And the reason is when a brain cell becomes low on energy, the brain eats it. Now, I know that sounds strange, but that's the key thing to understand. When a brain cell is low on energy, the immune system comes in and it eats the brain cell. So you're saying to yourself right now, that sounds weird. Why would the brain eat a cell that's low on energy? And I'll tell you why. It kills the brain cell by eating it in preference to allowing that brain cell to burst and spill out its contents and elicit a big immune reaction and kill a whole bunch of adjacent neurons. So in order to prevent the collateral damage of cell lysis, cell membrane bursting, it eats it before it's so low in energy that it dies. Okay, so in order to know when to eat the neuron, the immune system has to have a counting system to measure the energy level of the brain cell, and it does. And the counting system is called the phosphatidylserine externalization system. I write all about it in this book right here, Prevent and Reverse Chronic Fatigue. So what happens is phosphatidylserine is a phospholipid. Each cell has a phospholipid bilayer, and there's an inner leaflet and an outer leaflet, okay? So phosphatidylserine has to stay in the inner leaflet. And there's enzymes to make it do that called flippase and floppase. When you run low on energy, you start not being able to keep phosphatidylserine. I'll put a pen in my hand to indicate phosphatidylserine. Okay, so here's the phosphatidylserine, and it's going to flip from the inner leaflet into the outer leaflet. And when it starts flipping into the outer leaflet, there's a protein in the brain called complement that will bind to it, and then that's like a neon sign: eat me, eat me, eat me. Okay. So why does this all happen? What happens is it has to be a physical binding in order to activate the neon eat me sign, because you can't just release a chemical, because the brain has 100 billion neurons and 10 times more supporting cells. If you released a chemical, it would diffuse all over the place, and the microglia, macrophages, guard cells of the brain wouldn't know where to go. So it has to be a physical finding, complement bound to phosphatidylserine externalized, to eat that brain cell. To eat it before it runs so low on energy that it can't maintain its ionic plasma membrane gradients, and it would lyse. That means burst open, and then all its inner contents would spill out and create this giant inflammatory reaction. And that's why you can't see anything on microscopy. All you see is the decreased number of neurons, because it's been eaten before it bursts. All right. So again, you need ATP to maintain phosphatidylserine internalization, normal position, through the enzymes lipase and flopase, or you end up with this, okay? All right, so that's why brains shrink. The next question is, well, what about the hypoperfusion hypothesis of Jack Delatorre? That's the thing you should learn first. Jack Delatorre was a brilliant guy, PhD, out of Texas. He tied off the internal carotid artery in the neck of a mouse. 2 months later, middle-aged and older mice become demented. Okay, he repeated this in multiple ways. Tied off both carotids, tied off the carotid and the vertebral arteries, tied off the middle cerebral artery inside the brain. And every single time, the vascular territory supplied by that vessel, which at autopsy found it was shrunk. He initially expected a stroke on the same side he tied off the carotid, but there was no stroke. It was just a shrunken brain in the vascular territory supplied by that vessel. Okay? So he called this the hypoperfusion hypothesis. Perfusion means blood flow, so hypo means decrease. So when you decrease blood flow, you decrease oxygen and glucose delivery to the neuron. And then the neurons gradually die. A stroke is when there's a big blood clot and you suddenly decrease the blood flow completely, then those cells just die. But if it's just gradual, there's still collateral flow, like, blocking the main route in the highway, some collateral detour flow will still get there. So it gradually dies. And at first you'll say to yourself, well, not that many people have a severely stenotic or occluded internal carotid artery in their neck, and that is true. However, tons of people have intracranial atherosclerosis from chronic diabetes and hypertension with the development of atherosclerosis. Tons of them, most of them. I look at brains, necks, and chests every day, and I see tons and tons of atherosclerotic calcifications. Tons of them. All right, it's almost like I joke they were internally turning to stone. So now, let's talk about what I call mouse equivalents. If you have poor pumping pressure from the heart, congestive heart failure, you're like the mouse, global hypoperfusion, okay? If you have atrial fibrillation, you're dropping the pumping pressure to the brain, global hypoperfusion. The drug companies are always trying to drive down the threshold to treat on hypertension, because then they can sell tons more drugs. So if you overtreat hypertension, too much drugs, drop the pressure too low, you're like the mouse equivalent. You underperfuse your brain. Why do you have a blood pressure? To pump blood to your brain, to the top of your cerebral cortex against gravity. Okay, then, I read all about nutrition. None of these other guys know anything about nutrition or toxicology. Okay, so if you eat a high-fat diet, it sticks your red blood cells together. The LDL cholesterol, the chylomicrons, the triglycerides, they overcome the zeta potential, sticking the red cells together, so your blood becomes thick like a milkshake. If you're pumping thick blood, you have to increase pressure to get it up to the brain, okay? Well, then you're going to be like the mouse. You're going to drop the oxygen and glucose delivery. Okay, your pressure is going to have to go up. That's going to damage the arteries, all right? But even just having the red cells bound together by the fats, that will drop oxygen delivery. And we can remember that from the papers. Peter Kuo showed 15 to 20% of decrease in oxygen delivery with a high-fat meal. Roy Swank showed a high-fat meal will drop oxygen glucose delivery up to 30% in hamster brains when he measured it. And it's even worse when you have sodium, because then you vasoconstrict, so the pressure has to go up more, but you're inhibiting endothelial nitric oxide synthase, so you're going to decrease vasodilation in the brain, so that's going to drop your perfusion of oxygen and glucose delivery to your brain cells even more, okay? And then, I started reading all the papers on caffeine. Caffeine drops blood flow to the brain 15 to 25% to the cerebral cortex. So you're dropping it with that. So think about what the typical dumbass eats, okay? They'll eat a pizza, super high in fat, super high in sodium, and then they'll have, some type of caffeinated drink, Coca-Cola or something. So now they cranked up the caffeine, and let's say they're stressed out about their job and they're sleep deprived, or they'll have some coffee or something too. They're doing everything wrong. They're vasoconstricting, dropping the blood supply to the brain, dropping the oxygen carrying capacity of the blood with all that fat and with all that sodium. And then simultaneously, from the stimulants, the caffeine, sleep deprivation, and stress, they're ramping up the glutamate transmission across their synapses, which is an excitotoxin effect. Because glutamate's 90% of cerebral cortex neurotransmitters, and it's excitatory. So you see the screw job happening here. You're increasing the metabolic rate while you're simultaneously dropping the oxygen and glucose delivery. That's the one thing I figured out, too. Delatorre just figured out you drop oxygen and glucose delivery, the neurons are going to have trouble. And I sort of made the point, well, it's not just dropping the oxygen and glucose delivery, it's also simultaneously increasing the metabolic rate, so you're widening the gap between the available oxygen and glucose delivery as well as the metabolic rate of the neuron. And there was literature that came out about excitotoxicity. And it started with John Olney in the 1960s. He coined the term excitotoxicity, meaning an excitotoxin is something that ramps up the metabolic rate of a neuron. And he got that from injecting MSG, monosodium glutamate, into rat brains, okay? And then the rats would have seizures. And as he studied it more, he realized this MSG was being put into baby food, okay? A major brain toxin being put into baby food. Not good. Coming out of an aluminum can. Not good. With a BPA lining, another neurotoxin, mitochondrial inhibitor. Not good. Okay, so anyways, other people did a lot of research on excitotoxins, and that includes the work of, sort of your conventional scientists, people like Dennis Choi, Mark Mattson, and others. Russell Blalock was frustrated because he felt that this excitotoxicity was related to his father's death from Parkinson's disease. And then it was noted other things also have an excitotoxin effect. We talked about caffeine doing it, stress doing it because it increases glutamate as well. It's not the monosodium that matters, it's just the glutamate that matters. And now they put manufactured free glutamate, which is the same thing, excessive glutamate in all the processed food, almost all the processed food. Sleep deprivation raises the same hormones as psychological stress, cortisol and catecholamines, that will increase glutamate transmission across these neurons and will vasoconstrict cerebral blood flow, dropping cerebral blood flow. Turns out glyphosate is also an excitotoxin because the NMDA receptor, the calcium channel on the postsynaptic neuron, the one that glutamate binds to, has a coincident detector, meaning it simultaneously has to bind to glycine in order to be opened up. Well, guess what? Glyphosate is like glycine phosphate, and that also is thought to activate the NMDA receptor, increasing calcium throughput, increasing permeability of that receptor. And guess what else does it? Beta amyloid protein. Well, where does beta amyloid protein come from? It comes from diabetes, from eating high-fat meals, type 2 diabetes. When you cause insulin resistance, you get hyperinsulinemia because you have insulin resistance in the periphery, the body. Okay, so what happens is the insulin-degrading enzyme of the blood not only clears out insulin, it also clears out beta amyloid protein circulating in the periphery. Periphery means the body outside of the brain. So what happens is it can only be made in fixed amounts, insulin-degrading enzyme. So when you have insulin resistance from high-fat meals, you get the insulin-degrading enzyme used up. It has higher affinity for binding insulin to clear it out of the blood than it does for beta amyloid protein. So now beta amyloid protein accumulates in the peripheral blood. It crosses back across the blood-brain barrier, goes into the brain, and it activates the NMDA receptor to open it up, making it increase permeability. Oh, the other thing, too, knowing nutrition. It really helps to know nutrition to understand disease. The vast majority of Americans, over 90% of them, are magnesium deficient because they don't eat plants. Because they're magnesium deficient, they increase permeability of the NMDA receptor, because normally magnesium sits right there in the center of the NMDA receptor, blocking it, okay? It's attracted to the negative 65 millivolt plasma membrane potential. Inside the cell, it's negatively charged. So the positive charge, 2+ of magnesium, is attracted to that. But once you partially discharge the cell through the AMPA receptor, glutamate binding to that first, it's a sodium channel, then the magnesium moves away. But people who are magnesium deficient, that channel is open, okay? It opens much more readily. So that has an excitotoxic effect. That's another reason why magnesium is called the M for magnesium, M for mellow out. It decreases anxiety, decreases stress, improves sleep. Because it's blocking your NMDA receptor, your calcium channel. Anytime calcium is elevated in the cytoplasm, the neuron becomes activated. So magnesium lowers cytoplasm calcium and thus mellows you out. That's what you want. Okay, so anyways, this was all this work done to figure out a lot of these things on excitotoxicity. Martin Pall also, earlier researchers figured out that EMF, electromotive force, like from cell phones, from electricity, from Wi-Fi, from anything electrical, was increasing, opening up voltage-gated calcium channels, okay? And then he also figured out an extension to that through oxidative stress called the no pathway, the nitric oxide peroxynitrite pathway, which sort of contributes to all of this as well, okay? And then I read some books about sarcoplasm, endoplasmic reticulum, calcium ATPase, which is also the endoplasmic reticulum inside a neuron is a calcium reservoir, and you pump calcium from the cytoplasm not only back out into the extracellular space, you also pump it into the endoplasmic reticulum. And when SERCA is inhibited, which it gets inhibited by diabetics and a few other things, you're going to decrease the ability to get calcium out of the cytoplasm, which is the equivalent of excitotoxicity because you're going to increase the cytoplasm calcium concentration. Okay. Then there's the theories that Tetsumori Yamashima, MD, PhD guy he's on an Alzheimer journal, and he's a bright guy, Dementia journal. He figured out what's called the Calpain-Cathepsin theory of neuronal death. The bottom line is fried foods cause lipid peroxidation, producing toxic aldehydes like hydroxynonenal, which inhibits the heat shock proteins, which then causes lysosomal lysis. Very bad thing. And the lysosomal protease enzymes like cathepsin are sent out, and it damages the cell. Okay, so you don't need to be eating fried foods to damage your brain, but if you eat fried foods, you will accelerate the rate at which you damage your brain. And that's why also I really don't like the things all these high-fat phonies are saying, trying to tell people to eat more oils. That's a crock of BS, and what they're doing is a tremendous disservice to patients, okay? It is really wrong, okay? Lying to the pros, hurting the pros. When you lie to the pros, you hurt the pros. The pros are confused, okay? If you intentionally confuse them and make it worse, that's really wrong. And that's why I say Christianity is the only thing that could fix medicine, because it says tell the truth regardless of the money. And you need that, because otherwise there's just too much money. Everybody's going to sell out if they only care about money instead of telling the truth. Okay, and then the next thing that I figured out was I had known that diabetes is caused by inhibition of intermitochondrial membrane electron transport. And I know that diabetes leads to beta amyloid protein being elevated and excitotoxic effect. But I knew I'd come across little things in my reading that were also damaging the mitochondria. I'm like, holy crap, there's got to be more. I was going to be a biochemist when I was young, so I owned 7 biochemistry textbooks and a nutritional biochemistry textbook as well. And I went through all of them. I couldn't find anything on mitochondria inhibitors, so I just started studying the literature on my own. I found over 120 mitochondria inhibitors. And think about it. Remember what our problem was, a gap between the metabolic rate of the neuron and the oxygen and glucose delivery. But there's another factor in there if you want to make a triple axis. It's the ability to produce energy. So you need, over 90% of your energy is made in your mitochondria. So you need the mitochondria to work well. If you inhibit that mitochondria by all these common things, antidepressants, tricyclic antidepressants, selective serotonin reuptake inhibitors, antipsychotics, Haldol, antibiotics, aminoglycosides, fluoroquinolones, beta-lactams, tetracyclines, a lot of cardiac drugs, beta blockers, statins, metformin, tons of drugs. Fluoride's a mitochondrial inhibitor. Mercury is a mitochondrial inhibitor. Aluminum is a mitochondrial inhibitor. Arsenic is a mitochondrial inhibitor. Cadmium is a mitochondrial inhibitor. Tylenol is a mitochondrial inhibitor. Propofol is a mitochondrial inhibitor. Cyanide, as in cyanocobalamin, as in almonds, as in potentially supplements for creatine, as in potentially supplements of vitamin D, as in flax. Okay, I don't want any of that stuff, all right? All of these things are adding up. And BPA, a lot of these estrogenic chemicals, BPA and atrazine are also mitochondrial inhibitors to drop energy production. Because the poor neuron is screwed. You're dropping its blood flow, you're inhibiting its mitochondria, you're inhibiting its SERCA, okay? And then how's it going to meet its metabolic demands? You cranked up the metabolic demands, dropped its blood flow, and you dropped its ability to produce energy. The neuron is screwed. I made the metaphor. It's like, imagine you had a slave, okay? You told the slave, you must work harder, but I'm going to cut your food supply. I'm not going to let you sleep as much, and I'm going to whip you in the legs and tell you to run faster. You'd be like, what the hell is that? It's insane. We abuse our brain cells, okay? And that's why they can't survive, because it's a supply and demand problem. We've cranked up their energy rate, and they have to meet that or they're going to die. They're going to get eaten by their microglia. And then we drop their ability to make energy, and we drop their oxygen and glucose supply of substrate to make energy from. Okay, and we messed up. So we're screwing over our brain cells. The average American is. And the only way to break out of this is, I've talked about it in my lectures. Stop eating the bad stuff, avoid the toxins, filter your water, eat organic only, manage your stress, be religious, get your sleep, etc. So there it is. This is called the Rogers supply and demand theory. That the neurons die because their metabolic rate is increased, but their blood flow is dropped, and their mitochondria are inhibited, their SERCA are inhibited, and sometimes there's secondary problems going on as well with fried food and EMF. So the poor neuron is screwed. And that's why I just see one after another demented patient. I see tons of, by the time the patient's 60, I expect them to be mentally slow. And I see quite a few mentally brain damage patients with cognitive impairment in their 40s and 50s as well. But after 60, I expect the average Western patient to be mentally slow. So anyways, there it is, Rogers' supply and demand theory of dementia. And I'm the one that figured this all out. This is the best theory in the world for dementia. Don't even kid yourself. I've gone through the Harvard textbook, 1,700 pages. They're a joke. They'll have 1 or 2 paragraphs on excitotoxicity. That's a joke. There should be, like 50, 60 pages on it, okay? They're a joke. Conventional medicine is match the ill to the pill and send a bill, okay? And these research foundations have all sold out. They're atheistic Darwinism. They're just playing games to get their money. There's a whole bunch of books written about what a joke Alzheimer's research is. And you can watch, there's tons of videos on there, and you'll watch these guys, these researchers telling you that they can't tell what's going on at autopsy. And I just explained it all from looking at all these brain MRIs. And what I said, you know what's unique about it? It tells you what to do. In my longer lectures, I go through all the other excitotoxins. I go through all the SERCA inhibitors. I go through the things that drop cerebral blood flow. I go through all 120 mitochondria inhibitors. It's all in my books, and you'll find it in my other lectures. So if you really want to know how to prevent it, because the other guys, they're nice. I know there's some neurologists talk about Alzheimer's. All these neurologists that talk about Alzheimer's, they barely say anything. They give you some wimpy bullshit and they tell you to drink olive oil. They don't even know what they're talking about. And then me, I'm the guy who figured out all this crap. I'm the best brain doctor in the whole world. I figured it all out, and I explained to you right here how I did it. And nobody wants to talk to me. And then they'll have Mickey Mouse guys like Andrew Huberman. He's reading out of an undergraduate textbook, a sophomore biology major level textbook, and they go, oh, he's a great neuroscientist. BS. He's Mickey Mouse, baby talk. You can have a triple fellowship trained neurologist. I don't know twice as much about them. I got a bunch of neurologist friends and I like them, but I'm the one who teaches them about how this stuff works. All right. Anyways, there it is. I hope you found it helpful. And if you're trying to prevent cognitive decline in yourself or in a friend, watch my other lectures or read my books, and you will see I explain exactly what you do. It's not rocket science. You just have to do these things. And naturally healthy populations, they do this automatically because they eat whole plant foods that are all organic. They exercise a lot. They get their sunshine. They manage their stress. So anyways, I hope you found it helpful.